Good afternoon, everyone. Today we'll do section 9.1. This is some really cool stuff on confidence intervals. We're going to be estimating the population proportion using statistics. So this is inferential statistics, what we're getting into right now. This is inferential statistics. We're trying to estimate what's going on in a population. So sometimes you're talking about millions of people, millions and millions of people. So how do we do it? Well, we go out and we get a sample. We get a sample that's representative of the population. It could be just 1,000 people though. But from that 1,000, and we do it by simple random sampling. From that 1,000 people we obtain, we can make inferences on what's going on with the millions, right? We can really get an idea of really what is that population proportion. We'll never be 100% perfectly accurate, right? But we estimate, and that's what we do in stats, right? It's far better to estimate something. It's something like a really cool question, a really cool problem, and get the exact answer to something in this world that's just kind of, basically lame. So in this case, that's what we do in stats. We estimate. We'll have a certain level of confidence with this. So we're going to be doing confidence intervals about a population proportion. The title in your book, they titled Estimating a Population Proportion. They thought that'd be more appropriate for the student to understand. That's what we're really trying to do. We're trying to figure out this thing. I'll put it up here. It's called REL. It's the population proportion, but we don't know what it is. And these questions get posed every day. That's what's so cool about this section. So you can go online after class and just pop up like any professional polling site. It could be Gallup polling, USA Today, it could be Rasmussen reports, Quinnipiac, any of these polling places, and see what polls they just ran in the last week. And there'll be questions. It doesn't have to be politics, everyone. It could be anything. But you can look in there, and they're using everything we're going to discuss today. So you can imagine most people read that stuff. At the very, very end of their article, they're going to talk about margin of error, level of confidence. Most readers probably have no idea what they're talking about. They ignore that. And they're just like, okay, what's the proportion? That's what they're focused on. You'll understand it exactly. You'll know where it comes from. So that's what's pretty cool. So I could grab a problem out of the textbook, absolutely, and do a problem. But those problems in the book, every poll done in that book, it's probably about 3 years old, true? So I figured I'd go online, grab a poll that was done in the last week. So that's what I did, and that's the question we'll start with today. A poll was done. And this was the question was, they asked, in terms of the next election, all right, is the issue of abortion important? And they called people, they did it randomly, everyone, they did simple random sampling, they called people on the telephone, asked them this question, and this is how they responded. So, is the issue of abortion important to you? I'll just put quotations out. This is the question was asked. So 1,000 likely voters. We're asked this question. Is the issue of abortion important to you? Oh, it's in the next election. Wait, just put that. When voting in the next election. The question mark right there. All right. Is the issue of abortion important to you when voting in the next election? Then they asked likely voters. So that means that they made a phone call to someone, it was a random phone call, and the person answered, and they probably asked them a few questions first. When was the last time you voted? And the person was like, oh, I haven't voted ever. Do you plan on voting in the next election? No. It's not worth my time kind of thing. Well, then that person would be a part of this poll. So that's when they had this likely voters. All right. So if they call and the person answers, what, 13 years old, right? You're like, okay, so they're 13, so they're not a likely voter. So 1,000 likely voters were asked this question. They were sampled, this sample here, the 1,000 people. This is a random sample. I do want to point that out. And this isn't made up. If you want to know who did this, it was Rasmussen Reports. Rasmussen Reports did this polling right here, did this survey. All right, so this came out of this. 700 out of 1,000 responded yes. And the other 300 responded no. And we're going to construct a confidence interval about what is the proportion. See, that's just 70 out of 1,000. And what we're trying to do today, Owen, we're trying to see what's going on in the entire population. All likely voters in the United States. So we're talking about millions of people, right? But that was only what? Just a group of 1,000. It's a big difference. Well, that's how we do it, and it's called inferential statistics. So the first thing we're going to do before we run and construct the confidence interval, the first thing we always do, everyone, we're just going to verify our requirements for this. All right? So we're just going to verify any requirements before we look at this, and consider, hey, whether or not is the distribution of the sample proportion approximately normal. And you go, oh yeah, aren't there some checks for this? And you probably remember this from last class, everyone. The checks for this are, one of them is
NP2.
Good, NP2. The book writes NP 1 minus P, just like that. And then when this is really right here, that's really a row. So if you want to go N times rho times 1 minus rho. An easy way to remember it is just N and P and Q. But it has to be greater than or equal to 10. Right? We got a random, they already said it's random, so we're good there. That's one of the requirements. It's a random sample, I'll list that. But this N times this rho times 1 minus rho has to be greater than or equal to 10. That's one of the requirements we got to make sure is going on. So that the distribution of the p hat that we're going to look at is approximately normal. All right? There's one other one, so I'll put a comma. The sample size has to be less than 5% of N. Oh my gosh, do not let this annoy you. This is absolutely going to be true, everyone. We can check it. Big N means the population size, the size of the population. Are we talking to millions of people?
Yep.
Big N is like all likely voters. So you and I are like, in the U.S., my gosh. So with 320 million people in the United States, so likely voters, well over a million. We can use a million, it's going to be good to go. So we'll be checking that off. I'm going to put one more thing. They did say it was a random sample, so we have that good. So random sample. Some students just write SRS here for simple random sample. Just to represent, yep, it was a simple random sample. Hey, so before I go on to B, we're going to construct the confidence interval. This stuff's a lot of fun. In the end, we'll talk about fast ways to do this on a calculator. I know you like that. There's something really important. Some of you might have spotted it already. This is what we've always done for our checks, right? Mm-hmm. We did, the last section we covered was 8.2. And you all did a great job with this. You're like, oh, just got to check this. We're like, well, hold up. We're like, stop. We don't know that. So right now, when this whole question is, we're trying to estimate what? This thing. I mean, I'll go over here and go, we're estimating, we don't know what this is, question mark. We don't know what rho is. And look what the first check is. It's like it's in the check. So I want to tell you what we do in confidence intervals. Because we don't know this yet, we're going to use our p hat here instead. We're going to use p hat as in place of that because we don't know rho yet. We're trying to estimate it. Right? Now, if someone had never did this before, you can just use, sometimes people just use 50%.
No, but shouldn't that be, it's kind of binomial too, because 700 said yes, the rest likely said no.
That's right.
So 700 over 1,000?
That's very good. It is. They didn't have any like, are you in between? Not sure. So Art, that's good. So and we're really going to look at n times p hat times 1 minus p hat. Now somewhere in the wording up here there is a p hat. And I always encourage you to write it off to the side somewhere. Let's go off to the side. What is p hat in this problem? We don't know this, but someone did a sample, right? They did a poll. There's 1,000, there's a 700. I'm going to go off to the side here. What is this p hat? What's it equal to? Remember the formula? X over n. Good. We'll just see what it is. I think it's great. You write it as a decimal, because this will be a fraction.
0.7.
700 out of the 1,000, which equals 0.7. I'll just keep this off to the side, because we'll need that just to, verify our parts. Cool. All right. So I'm going to do that. You got a calculator nearby. What's 1,000 times 0.7? What's 1 minus 0.7?
0.3.
Good. Unless you like to type 1 minus 0.7. You got it. I think we're good to go, right?
210.
210. Holland, thank you so much. Isn't it well above 10? Check. This is going to be true. I want to check it. We can do it, but this is going to be fun. By the way, a lot of these polling places, Gallup, CNN, USA Today, all of them. Quinnipiac, a lot of times they're sampling about 1,000 voters. So it looks like a lot of times they're going to be good to go, aren't they? That's why. They're not sampling 30 or 40. They wouldn't reach this. The distribution of p-hat wouldn't be approximately normal. Now you might be curious, like, why are they only doing 1,000? Why don't they do like 5,000? So we'll talk about that. We'll talk about that today. Why don't they go get like 3,000 or 5,000? Well, let's see if this is okay. We've got our 1,000 here. Is that less than 5%? Heck, I'll just use 1,000,000. I'll just use 1,000,000. Big N, right? Capital N is well over 1,000,000. We're talking about all likely voters in the U.S. It's well over 1,000,000. If you just do 0.05 times 1,000,000, you're still going to be fine. That's 6 zeros, right? I mean, what is 5% of 1,000,000? You can hit on a calculator. Just see how big it is.
50,000.
50,000. We didn't poll 50,000. They only polled what? 1,000. I mean, we were fine. So that's always going to be good in terms of these polls. Unless someone goes out and goes, oh, let's go sample 75,000 people. So we just have to check that always at the beginning. We're just making sure. Was the sample size really big enough? So that this comes out and you go, what is this telling us? This whole idea of verify requirements, so it doesn't sound so goofy and abstract, is the distribution of p-hat is now approximately normal. So we get to use the bell curve. And we get to use that normal CDF stuff, everything we've been doing before. Even the inverse norm button off the calculator. It's approximately normal, okay? All right, so now we're going to go to B. Here's the fun part. And we're going to construct a confidence interval. Just going to write construct a confidence interval. If you don't like the verb construct, you could replace that with compute. I mean, the author uses the word construct. You could say compute. Well, we're going to construct a confidence interval. We're going to get a couple numbers. It's an interval, everyone. An interval is like, something like this. 12%, comma, 17%. When I tell you, you're going to get something like this. And you can write them as decimals, too. We'll see what we get in our math, but you get stuff like this. When we're talking about intervals, whoops, you get stuff like this. Like 0.12 to 0.17. We'll see what we get. Now, that's coming up. So we're going to construct a confidence interval. I'll create the formula when the formula is available in the book. The formula is even on the formula sheet. Heck, even before you leave to that, I'm going to pass out copies. Like, what are these formulas? Can I see these? You can have copies of this. So I like to construct it with you. The first thing you go, how do they get this thing started? We're trying to get this in a math formula to figure this out. Well, they start with something called a point estimate. They start with something called the point of estimate. We're going to right here go ahead and put CI and put an equal sign. CI stands for confidence interval. You go, what do they start? They start with something called the point estimate. You go, what's that? The p-hat. That's where they begin. But it's like your point. We need some focus point, some paramount point just to begin with. Oh yeah, use your p-hat. Use that as your starting point. So this is called the point estimate. All right. Then we're going to add and subtract. I'll put this in words. How many standard deviations it is away from that p-hat.
Yes, okay.
Okay? So that's what's going to go here. How many, after the plus minus, a math formula to represent how many standard deviations we are away from the p-hat. So we add or subtract it. So it's the plus or minus. You go, what's the standard deviation? So now I got to use the standard deviation formula
P-hat.
for p-hat. And this is coming from 8.2. Okay? And you go, what was that? Do you remember this? It had a
PQ over
P, and then a 1 minus that divided by the
N.
n. Or rho times 1 minus rho over the n. But again, everyone, something funny's going on. We'll catch it right away. Do we know rho?
Yeah.
Do we know what rho is yet?
No.
This is what's funny about this section. We go, we don't know it. So what are we going to use in place of this every time in this section?
P-hat.
Yeah, we're going to use p-hat. So when you put your little p-hats, little hats on that p, little hat on that, or you can call it p-hat, q-hat. And when if that looks too complicated for you, some statisticians just like to write it like this. P-hat, q-hat over n. Because it's easier to say and easier to remember, if you prefer that. But that's how it's written on the formula sheet. Now, I left some space here because I got to put something here. I said p-hat plus or minus how many standard deviations. So for how many, that's where we, remember we said, oh, you're 1 standard deviation above the mean or 2 standard deviations below the mean? Right here is what's called a z-score. So put a z right before this. Let me make sure this is all level so it doesn't look all like scattered and stuff. I'll make sure, I know a lot of you are copying this. We get this all nice level. This is, you got a p-hat, and then you got a plus or minus. Then you got the z-score multiplied to the square root of p-hat times 1 minus p-hat divided by n. This is the confidence interval formula that we're going to use throughout today. Over and over and over again. This is it. And it's available for you. So like, I don't memorize that. That's totally fine. Let's see how many numbers we already know. Do we know that?
Yes.
All right, that's our point, which is the what?
0.7.
All right, 0.7. And when I'm going to leave the z last, because we don't know that yet. Because I have to give you a certain confidence level, and I haven't expressed that yet either. But at least we can do this part. Square root. This is a 0.7. I'm going to hit multiplication, okay?
Mm-hmm.
What's 1 minus the p-hat?
0.3.
And then we divide by the
1,000.
1,000. And we'll talk about z. And when to get z, something else has to be provided for you. It's the level of confidence. How much confidence do they want us to do in here? So for my problem, for the first problem today, I'm going to say construct a 95% confidence interval. All right, so first I just wanted to write it that we're going to construct a confidence interval. This is a confidence interval. But it has to be specific, and they have to present that to you in the textbook. All right, we're going to construct a, right before this, I'm going to write a 95% confidence interval. All right.
You said that's always in the beginning?
Always. And Liz, really good question. So you're not worried about this. They will always give you the level of confidence at the beginning. Now, if you go out in life, for some reason you're doing something, you're like, you're working on your bachelor's degree or your master's degree, and all of a sudden you're like, oh, I got to do some statistics. And you got to your poll, and you do your confidence interval. You might just say, all right, I'll do a 95% confidence interval. And you go, why is that? Do you remember, everyone, what's 100 minus 95?
0.05.
But 5%, we considered in this textbook anything under 5% was like almost unusual. All political polls are done with 95% confidence. So I'm going to say that again. Every political poll out there, you could check them. Go and Google everyone. There's somewhere in the article, it's probably in small font though, way at the bottom, they go, this poll was conducted with 95% confidence. Look it up. They're all done with 95% confidence. Not everything, everyone. I can't say every poll in the world. What if someone's studying something in terms of medicine, and they're using a drug, and they want to be really, really, really sure about something? Well, then they might use 99%. Does that make sense? Yeah. Whereas something maybe isn't so important, maybe someone will use 90%. A lot of them are like 90, 95, or 99. Most are 95%. The textbook, you know, they just keep throwing things at you when you practice them. So don't be surprised when you get a 96% confidence interval. I'll show you how to get to the z. So anyone cover that? So right now, we're trying to get the z value, and it's going to come from the what? This number right here. So I'm going to underline it. But it isn't 0.95. To get the z, everyone, you and I have to draw a picture. So remember I went off to the side and did this? Mm-hmm. Let's go off to the side and draw a picture so we can figure out z. Okay? We go off the side. Here we go. Make a bell. Yep, p hat is approximate normal, everyone. And what's that p hat? 0.7. Now when you can put 95% from the middle. I'm going to shade. 95% shaded from the middle. Oh, it doesn't have to be a perfect sketch. We just got to get a sense of how we're going to get this z value. So when we didn't use this button often, in section 8.2 or section 8.1, we're now going to use this often. We're looking for that z value right there. Right there, and I'm going to put, what's z? I need to know it. Or I need this.
Oh, you do the inverse now. Yeah.
There you go. And when the function, if we're going to use the calculator, if we're going to use the TID3 and 84, most of us will, we're going to use the inverse norm function. It's going to be real simple. The only thing is that when you use this function off the calculator, you have to put into the calculator the percentage right there on the left. Cool. By the way, these are both going to be the same number, true? Except one's going to be negative and one's going to be
positive.
We can use either one. I like to use the positive. And when you go, are you serious? Oh yeah. You go, why does it not matter if he's a plus or minus? Because what's right before the plus or minus? Plus or minus. A plus or minus in math of a positive is the same thing as a plus or minus of a negative. I always use the positive one, everyone. So when we get these yours, feel free to just put a positive number there every time. That sound good? Absolutely. We'll always put a positive number. We don't have to worry about it because there's a plus minus before. All right, so to get this, everyone, yeah, what did they do back in the day? We looked in the back of the book. We pulled out a table sheet. They're back there. They're still there, right? And all these formulas, tables are still there if you like to use them. Are there colleges still to this day using those? Oh, absolutely. I think you can go down to UMBC. They probably got them out there. No calculator. You got to use the z-score and the z distribution. Or they go the normal distribution table. We'll use a calculator. It's inverse normal. And we're going to hit. Let me type it out so it won't get copied. The key is I want you to tell me what percentage to put in here.
0.25. 0.25.
We don't put 0.95. The way this is programmed into those calculators, we have to enter the percentage shaded in the bell curve accumulated from the left side. So everyone, some of you just do it in your head. I'm hearing Art say it, others are thinking it as well. You're like, that's just 2.5% right there, right? But let's show it in case someone doesn't know how to do that. How can we find that percentage right there? We start with everything has to add up to what? 100%. We subtract 95%. We're left with 5%, and then you divide that by what? 2. Good job, which is 2.5%. The only thing is, everyone, don't do this. 2.5, because how do we write these in the calculator?
0.025.
In decimal form. And that's 0.025, right? So in right here, I'm going to put 0.025, and that's all you have to put. You don't have to put anything else if you don't want to. You can just hit enter. Now we're going to go, where's this button again? Where's inverse norm? Oh yeah, it's in that second distribution menu. Let's go there. Whoop whoop. Oh, there it is. And I can just seriously put 0.025 and it'll give it to me. This number is going to come up so often, everyone. Don't be shocked that you just memorize it. Because a lot of these, Liz, are 95% confidence intervals. They're z-scores. So you go, 1.96 negative. I'm serious, you probably have it memorized. Now, if you want to go out more digits, you can, but I noticed after the 9.5, it did a couple what? Since it went 9.9, everyone, it's totally fine that you and I go write this as negative 1.96 or 1.96. And there you go. Now, I could have done this. Because some of you have, who's got the newer calculators? So you might go, all right, I hit the second distribution, I hit this inverse norm, and you put this 0.025, and you put comma the 0, comma the 1 for the z-scores, right? And you'll still get the same answer. Do you see that? So that's the default. You don't even have to put this comma. Oh yeah, the mean of z is 0. The standard deviation of z is 1, right? Cool? Hey, by the way, I will eventually give you a table. And right on the table, it shows that z-score. So I think it's funny, a lot of you, even though it's available in the technology, students don't mind tables. So I will give you a table eventually. And you might just go, oh, I'll just look this up. Or you'll memorize it. You know? So this came out to be what? Negative 1.96 here. So what's the z-score here?
Same, but
The same, it's
but
just
not
positive.
negative.
I just gotta enter one of these. One of the z-scores. I like the positive. So what I'm gonna put. Alright. So this is our confidence interval. We just gotta clean it up. We just gotta clean this baby up. This is it. This is the confidence interval. It's 0.7 plus or minus 1.96. Square root. Is it okay I rounded that? Because I always say never round to the end. Well, right after that 9.5 was 2 9s. This is fine. It is fine to use 1.96 here. Square root of 0.7 times 0.3 divided by 1,000. Now, Owen, can you put something in your notes? We'll keep calculating all this stuff. Do you remember what I called this? I know it's p hat, but you know what I call that? I call that the point, or the point estimate. Everything after the plus or minus, there's a name for that. You've heard this before in this world. This is called, the part after the plus or minus is called the margin of error. So I just want to put something here for your notes to say, from here to here, this number, we're going to get it. Everything after the plus or minus is called the margin of error. I write it as mo. The book sometimes just writes it as Z for error. It's the margin of error. That gets reported in the news articles. That gets reported on those polling sites. Rasmussen, or if it's a Gallup poll, they report this. We'll say the margin of error was, we're going to find out what it is. That's my point though. I'm sure people have no idea where that comes from. You'll know. It's coming from this math formula right here. Right there. Cool? Hey, so can we find this number first?
Yes.
So I'm going to hit the lights. I'm just going to do all that math. I can type it at once. It's not too bad. I'm going to do 1.96. Or I can use my last answer, right? Oh, and that's the part I like. Look, I'm going to use the ants button. There's the z. I'll use ants. Ants multiply square root 0.7 times 0.3 divided by 1,000. Close parentheses. That'll work, right? Gonna come out negative, that's okay, I'll write it as a positive. 0.028. Alright, I'll go to 3 decimal places. I'm gonna hit the lights. What's the margin of error? 0.028. A plus minus 0.028. So let me write this now. And here comes my CI. We've got it. It's equal to 70%. And when I'm going to erase this margin of error part, okay? Just to have room. Plus or minus 0.028. And I'm going to put a big box around it. There it is. That's it. That's my confidence level. Absolutely, you could write it like that.
So you keep the plus or minus?
And you keep the plus or minus, Mia. Good question. But Mia, here's my point. I want to say this. I encourage you, Mia, and everyone, to write this 2 ways. Like, that's an answer. Full credit. Absolutely. That's the confidence level. But I encourage you to write this 2 ways. Evan, aren't there 2 numbers in this mix? Yes, it's saying you take a 0.7, you add a what? 0.028. And we'll take a 0.7 and we'll subtract a 0.028. So there's really 2 numbers in here, right, Mia?
Yeah.
So I encourage everyone to write this way, and then again, put a parentheses. You probably did this. You take an algebra class previously. Remember these intervals, like interval notation? We always put open parentheses. I'm going to put the lower number here and the higher number here. So whatever's lower this, which one would be lower?
Minus?
Yeah, so when you take out your calculator, go 0.7, subtract 0.028, see what comes out. And I'll put that here.
0.67.
Ooh, 0.672? roughly 67%. And then I'm going to take your calculator, or if you do this mentally, 0.7 plus 0.028. 0.728. And me, I just encourage you and everyone, this is fine, but this is going to help us. You see we're on letter A and letter B so far. We've produced the answers to letter A and B. This is going to be a C and a D and an E now that apply to this. And if you write it this way, we're going to be able to answer a question. If we write it this way as well, we're going to be able to answer other questions.
So the lower the margin of error, the more accurate the polling is?
That's right.
Okay.
There you go. Now, I like to draw a picture to describe this. What's going on here? Who was in the middle? The p-hat, the point, which was 0.7. And what did we add? We added 0.028. And what did it produce? 0.728. And then we added what? Or no, so we subtracted 0.028 and we got this what? And we're saying with 95% confidence, everyone, and that's pretty confident. What's going on with millions of voters? We're never 100% confident, are we, in stats? But we're really confident. I mean, we're 95% confident that the proportion of voters, all right, who consider this abortion an important issue in terms of voting in the next election is between these, it's between 67% and 72%. Really sure. Cool? Awesome. All right. Hey, now, where is the margin of error again? It's anything after the plus minus. So I'm going to ask a question on that eventually. Oh, go ahead, Liz. Hey, in here, some students mistakenly think this minus this is a margin of error. The margin of error is on either side. So what is the margin of error again? It's this number right here, which is what?
0.28.
See that 0.028? That's your mo. I just want to point that out. Right there, that's your mo. So we're adding the margin of error, we're subtracting the margin of error. From here to here is your what? Your mo. Pictures help us see that. Helps us remember that stuff, right? All right, hey, great job with that. So there's our confidence interval. I encourage you to write it two ways. Now, put down letter C. Is the issue of abortion important to you on voting in the next election? 1,000 likely voters were asked. I can take all letter A out. I'll leave that. And I'm going to go up to letter C here. And when we are going to interpret this, we're going to interpret this confidence interval. We're going to interpret the interval in our own words. Like, what does this mean? I don't know. Let's see. This would be wrong. Listen to this. Interpret this interval. Between 67% and 72%, or 67% and 73% of the voters consider the issue of abortion important when voting in the next election. That's not right, because I'm just making that statement. I'm thinking it's accurate, true 100%. We have a certain level of confidence here. So what's our confidence level? So I'm going to start my statement with that. Ready? With 95% confidence. And then I'll put a comma. Does that sound good? All right, with 95% confidence, comma. So we got to state our confidence level. Oh, you bet all the articles do the same. When you read that at the end, they put it way at the bottom of the article. With 95% confidence, the proportion of voters who believe the issue of abortion is important. By the way, I'll write this another way too. I don't have to take all this out. Is important when voting in the next election. Or you could say, I said believe, you could say who consider. if you like that word better, who consider the issue of abortion. And voting in the next election is between which two numbers?
0.672.
0.672, you could do this. You like to write percentages. And what's the other number?
72.8.
It's somewhere in there, it's trapped in there. So with 95% confidence, we know the proportion of voters is in here. Hey, I'll abbreviate this too, because some students, I went back and referred to the actual question and stuff. Some students, Mia, will just go, can I just say the population proportion? You can. I'm fine with that. I really am. You write that on your paper, I'm fine with that. So once you're done talking, I'm going to write this another way, just an abbreviated way, which you might be fine with, but when I write it, I'm going to be careful that I don't mess up the wording. So I'll talk about that as well. All right, with 95% confidence, the proportion of, I put voters, it was really what kind of voters? Likely, so I can even put that in, the proportion of likely voters who consider the issue of abortion important. I take that off. Who consider the issue of abortion important when voting in the next election is between these two numbers.
Is this
That'll work.
Is this 95 like what we do it on the empirical formula that we had that thing?
That's right.
So we have like 68, 95, and 99.
That's right.
Three confidence.
And we're doing the two standard deviations away from the mean. Exactly.
Okay.
Very good. Sometimes they'll go for that 3 if it's something, I don't know, in the medical field. And you just want to be really, really sure, and they're going to bump it up to what? 99% confidence. Hey, you know what probably happens to the interval though? When you go for more confidence, right? It what? It usually spreads it out more. Hey, well, I'm just going to write this. You might find this easier. Interpret this. With 95% confidence, the population proportion is between 67.2% and 72.8%. Do you find that easier?
Yeah, that's much smaller.
You go, yeah, that's it. That's really what we're saying. Because the question's up there. You don't have to go repeat everything that was up there. We know that. But what's so important, everyone, don't say sample proportion. See, we're 100% confident about the sample. We did it. We got what? We know we did that, right? Yeah, we got 7. That's 100% there. We were trying to estimate what? This, with a certain level of confidence. Hey, by the way, sometimes people, they go, I don't understand what this means. What do you mean by 95% confidence? So, can I explain that to you? You don't have to write this down. I think it's important, as a student, what does this mean? 95% confidence. This is what it means. Everyone, if I repeated this and did this 100 more times, 100 more times in the next month, I just kept calling 1,000 people every day with a team of people. 1,000 people, 1,000 people, 1,000 people, 1,000 people, 1,000 people, 1,000. I did this 100 times. Everyone, 95 out of 100 of those, all right? 95 out of 100 of those would have proportions between these two percentages here. That's what it means. Can I say that again? Just so you get an idea of what I'm talking about. Okay? Ready? You go, what does this mean with 95% confidence? Because we're trying to estimate what's going on with millions of people, right? Throughout the entire United States. This is what I'm saying. If I continue to do this, and I did this 100 more times, I called 1,000 people today with a team of people tomorrow, the next day, the next day, the next day. I did this, 100 times. 95 out of 100 of those what? Those polls would have percentages between what? 67%, and that's what it means.
So that means...
Which really means it's somewhere in there.
That means 70 is, 0.70 is like a mean there.
That's right. It really is. Smack dab in the middle. We use it as the mean, as the middle. And we use it as this point estimate with some level of confidence. Isn't that cool? Everyone, great job at this. Great job at C. I bet you rock and roll with D. I would like you to calculate the margin of error. So I'm just going to put MOE. Can you find the margin of error for this book? And you look back at your work. And if you wrote it both ways, it's going to be a piece of cake, right? If we wrote it both ways, this is going to be a piece of cake. Brianna, remember we wrote the confidence in this way and this way? The margin of error is that number after the plus minus. It's hard to see it here, right? To do it here, you'd have to probably draw out a picture and take this and subtract that. But isn't it sitting right there? So that's why I encourage you to write it both ways. But you don't have to. I mean, you might find yourself just being comfortable writing it this way, right? And then you might go off to the side, maybe make a picture and just go, oh, I just got to take this endpoint 0.728 and subtract the p hat in the middle, and I can figure out what the margin of error is. Because that minus that will give you this what? 0.28. Hey, when you write this on your test, this is great, but you know what you probably should put in front of it? Plus or minus. Okay, I won't take off if you forget the plus minus. Or if you don't even want to do it. The articles even do it. I know, but even the articles put the little plus minus. Because they're saying margin of error means you what? You add it, and what else do you do? You subtract it. But you can still say mathematically, hey, the margin of error is about close to, if we round that, what would that be, 3%? By the way, that's what the article said. Makes sense, everyone. You got readers reading this article, of course, right? And your typical reader, 3% sounds better than what? 0.028. The more numbers you get in there, it gets more confusing. So they use 3% in that article. In fact, they're always trying to get this 3%. It just seems to be, you know, okay out there. As long as you get about 3%, that's cool. Everyone all right with that? All right, now this is fun. We're going to get into this discussion now, everyone, of why they're doing like 1,000 people. You know, and they're getting this margin of error like 3%. And maybe they could get it a smaller margin of error. Don't you all agree the smaller the margin of error, the better? You get a better estimate of what? This guy, you tighten it up. Tighten up that interval so we can really get an idea what this is. And that's pretty good. It's somewhere in here, right? It's in there somewhere. But if we want to tighten this, so that's the question, right? I want Rasmussen reports. Desires to, see this interval right here? Decrease the margin of error. I want this margin of error smaller. I want this interval tighter, right? I want to shrink this interval, tighter numbers, close together. Rasmussen for desires to decrease the margin of error. What do they have to do? What should they do? What should they do to decrease that margin of error? All right. Question mark?
Increase M.
That'll do it. All right, how'd you know that? That was really good.
It's inversely proportional, so N is at the bottom, right? So
Yeah, brilliant. And when you answer this question, I want you to see this. We're going to increase the sample size. That's the answer. This formula, I'm going to write it again over here. Look at this. What was the CI equal to? P hat plus or minus Z times the square root of this P hat times 1 minus P hat all divided by N. We're saying in this math formula, if you make this number right here bigger, it makes this number smaller. That's what happens in fractions. Art mentioned this word inverse. He's talking about this denominator here. If you make that number in the bottom bigger, it makes this whole number smaller. You want to see it? Watch this. 1/2, everyone. What's that number as a decimal? 0.5. Okay. Now watch this. What's 1/20?
0.05.
I just jacked that up a little bit, right? Guess what happens to this decimal?
0.05.
It gets smaller. You see what I mean? You explode the denominator, it makes it what? It makes this get what? Smaller. You make the denominator bigger, it makes it right. So the answer to this question, everyone, we'll keep it simple. Increase the sample size. Increase the sample size. Increase the sample size. We're going to increase the sample size. All right? Increase the sample size. Which is N, right? You know what some students do on a test? They just draw an up arrow, and then they put in. That's okay. I'm serious, right? That's what you mean? Hey, what are you doing with the end? You're gonna what?
Increase it.
Now here's what other students said. These are all appropriate. You're gonna have to call more people than 1,000 people. You're gonna have to contact more than 1,000 people. That's what they mean. That's what we mean. You need more people in this. So yeah, why don't they do that? Oh, and here comes that discussion I was seeking. Why don't they just call 5,000 people and all that stuff? Why don't they just do it? You'll get it what? Don't we want a smaller margin of error? Yeah. It costs money, doesn't it? That's the idea. This stuff, the people are getting paid to make these phone calls, right? It's a business. They got people working. And sometimes just to get more people out of here and get more phone calls, that requires many more days, many more man hours, etc. Costs a lot more money, all right? That's why. At least one major reason. But everyone seems to be okay in these political polls lives with 3%, which we got here. But now, and I'm going to get the letter F. So this is important. We're going to pretend that Rasmussen Reports does desire to get this smaller margin of error, and I'm going to give you the error, but you and I are going to do a backwards math problem and figure out, well, what's the sample size needed? And you'll see in your practice problems, I have many problems in the textbook already picked out for you on that list that are good practice problems for this, all right? So I'll erase this top part so there's enough room, and I'm going to call this letter out, okay? Determine the sample size. Necessary. So what I'm saying here, I'm going to ask this question is, Rasmussen, let's pretend they're going to go out and they really want to get this daggone number right here down to 2%. Okay? So the question is going to be regarding to how many phone calls are you going to make? How many voters are going to have to contact? So determine the sample size, which is what letter?
N.
N. So you're going to figure this out as N. Determine that sample size N. Necessary to obtain a margin of error, and we need to just put MOA, or ME. ME for margin error, right? Margin error. Within 0.02. Right now it's at like 3%, when it was 2.8%. Determine the sample size necessary to obtain a margin of error within 2%. Okay. You ready to roll? Oh, and I gotta state, we go, what confidence? Everyone, we're gonna use the same confidence level. So this is still with 95% confidence. All right? I'll put that in parentheses. With the 95% confidence level. So I didn't want you to think, everyone, do we have to change the z-score? Nope. We're still going to use the same z-score with the what? What was the z-scores? Negative 1.96. So we're not playing around like, do we want 98% now? No. Same confidence level, right? Same confidence level, 95% confidence. Are you ready for this? Can I erase this down here? Mm-hmm. Are you sure? Okay. This is always interesting. We'll look out here. Who likes algebra? Right, now do you notice not every hand went up? You've heard, that's okay. And when you heard me say this at the beginning of the year, I said, that's like 2 times in this class we got to do some algebra. Here's one of them. Now, if you're an algebra hater, there's nothing wrong with that. What we're going to do at the end is we'll record a formula, and then you're just going to remember the formula. But would you make a note when we get that formula? It's not on the formula sheet, okay? So just say, oh, I'm just going to remember this. So if that's my point, if you feel like, I don't like algebra, okay, we'll produce a formula that you can use. But I'm going to treat this as you and I are going to do a little algebra. So I'm trying to determine the sample size necessary, which is an N, to obtain a margin of error within 0.02. So I'm going to do this, and I got to go over this math formula here, and I got to extract the part of this formula here, which dealt with the margin of error. Where was it? Ooh, Brianna, excellent. It's this part. See this? Everything in there, I'll take this out of the way so it doesn't look confusing. This is your method. So that's the part I got to write down. I'm going to write that down. And I'm going to say, margin, this is what I'm going to do. I'm going to do an algebra problem. Margin of error equals
z, and then there's a square root, and there's a p hat, and there's a 1 minus p hat, and then there's an n. And hey, for the algebra haters, that's not the formula I'm talking about. Don't worry, we'll get a way better one. That's not it. That's not it. So margin of error equals z times all that. All right, let's fill everything in. You'll notice, everyone, the only thing we don't know is that. All right, what's the margin of error now?
0.02.
Good. Now, hey, just in case this happens on the test, if you accidentally right here, right, the original, remember we got 2.8% earlier? You do all your math, I'll tell you what you get for n, you're going to get the 1,000 people. Remember with 1,000 people, it came out to what? 2.86. This question is, what would be the necessary sample size to get it down to a 2% margin of error? Somebody use 0.02. Still use your 1.1.
96.
Because it's 95%, see right there, 99%, that's the z-score. I'll put a square root. What's the p hat? You go, what do I use there? We're going to use the previous p hat value that we got, which was what?
0.7.
Now, everyone in this class I know does this, because I get emails. Students come to me before class, up in my office hours, they stay afterwards, they ask me questions about it. You read the textbook and you practice the textbook problems, right? I have to tell you something. What if you did this math problem and there was no prior estimate? I want you to use 0.5 there. Someone got that? So if you hear this word, this is for the textbook. If they say there's no prior estimate, that means they haven't done a sample yet, then guess what you use right here?
0.5.
Use back nav, what's in the middle? 0.5. So only use 0.5 if there's no prior estimate when you're studying and practicing. But here we have one. What did we get earlier?
0.7.
So we use that. This is a what? 0.3?
Mm-hmm.
And look, everyone, I'm going to put it in yellow. What's our variable?
Yeah.
In algebra, they call it the unknown. So do you mind sticking with me for like 2 minutes on the algebra here? Remember I do this? I'm doing this in my O12 class right now, by the way. Seriously, we're covering this in chapter 10 of the Martin J textbook. To solve for this, everyone, I'm going to divide the 1.96 on both sides, right?
Mm-hmm.
Okay. And here comes some algebra, and I get this. I know it's just an algebra problem. Don't worry if you hate algebra, we'll create a formula. Now I'm going to get rid of the square root t. I bet you know what I have to do. If I get rid of the radical, I got to do something to both sides. I bet you know. Right? Hey, it's like, I don't want that. I'm trying to solve for that. I want to get rid of this hat. I'll just, right, square both sides? Yeah. That, exactly. I'll just take this number, everyone. 0.02 over 1.96 on my calculator. I'm going to square it. And what happens is, you square a radical, and that radical goes away. See? Almost there. I've almost got it solved, but now, everyone, I'm trying to solve for n. It's in the denominator. I want it up in the numerator. So what I'm going to do is multiply n on both sides. So here I go. I'm going to multiply an n on both sides. I'll continue here. And I'll multiply it to the numerator. All right. 1.96 squared. I'll multiply it on this side. And it disappears off the right side, right? Look at this. See how it disappeared off this? Comes over here. Right? It's gone, look. I multiplied it on both sides of the equation. So my last step, here it is. N equals 0.7 times 0.3 divided by parentheses 0.02 divided by 1.96, and everything in that parentheses is squared. And we're going to get a number. We'll do it with our calculator. Now, and we're going to do this on the calculator. Now, algebra haters, I know, like, hey, or you're just like, maybe you like algebra, you're just like, can you just give me a formula? It's a lot easier. I don't have to do all this what? Algebra. Okay, here it is. The formula is n equals, what was that called? P hat, what was this called? Q hat, all over margin of error divided by z, and then what? Squared. So, and this is for anybody, put that in your notes. That always produces the sample size. P hat times Q hat divided by parentheses mo over z squared. Because that's the mo, that's the z, that's the square. This works every time. And so we do that, Brianna. Yeah, you don't have to do all that algebra. That's for anybody in here. This is fun. The only thing it's not on the formula sheet. That's the idea. You're like, okay, I just have to know that. Hey, I'm going to do this now. Everyone, can you make a prediction?
2017.
This number I get, is it going to be higher or less than 1,000?
Way higher.
It's got to be higher, right? If you get 1,000 exactly, it means you made an error and you accidentally used the .028. All right, so I'm going to hit the lights. Notice it's easy to type in. I go in here, and here it is. I go in here, I hit this blank screen. Okay, blank screen. P hat times Q hat, division symbol, parentheses, margin of error, over, what was the Z?
1.96
1.96, close parentheses, and then I want to what?
square.
Square. See that? I mean, it's not hard to type. I mean, I barely had to hit any parentheses. I only had to put the parentheses around the .02 divided by 1.96. Now this number, everyone, should be a higher than 1,000. And surely it is. It's up at now what? Now keep in mind, this is 2,000.84 people or persons.
So
Can you have 0.84?
no, so next
So always round up to the next. Always round up. What would that be rounded up?
2017.
2017. No, never round it. We round up so it gets within. We always round up so it gets within. That wording within. If you round it up, you always get it within. So I'm going to go to the next integer, which is 2017 likely voters. Now, everyone, I think you have a sense why these polling places don't always do 2%. Won't that cost twice as much money? Do you follow me? Just to go from 3% to the little 2%, just to move a tiny percent, it will cost them twice as much money, hours, etc., just to get there. So it's kind of like what's acceptable in these polling places and what we get from these polls, 3%. 3%. Isn't that cool? Hey, now this is the most important part today, I think. You go, is there a faster way to do all this what? All this stuff. Right, Autumn?
Yeah.
Autumn's like, come on.
Why are we gonna do that in the first place?
I'm like, come on now. Now this one, absolutely, Autumn, you can always use this, right? We can always do that, right?
Yeah.
But let's go back to letter B.
Oh, Lord.
Hey, can I erase this algebra? I'm gonna lead up.
Yes.
Get it out. Get it out. Hey, I'll tell you what. Autumn, have no fear with this. Because you'll find that this is not hard to do right here. If they have like a P hat at 63%, you get your Q hat, you get your margin on a Z, it always works out. Now, I'm going to go back to letter B. What do we have to do in letter B? Ellen, what are we going to title this now? What, fast? Autumn's going to put it as, this is my way. This is a fast way, right? To do all these computations. Ellen, welcome to, we know about this. What's the theme of our course? Don't let all the tedious algebra wear us down. Most important to us is interpretation. Most important to us is interpretation and understanding what everything means. But let's use technology to facilitate the tedious what? Computations. True? I know. All right, so we're going to start out. What was the first thing we had to do? Construct the what? And what level was it?
95.
Okay, good. All right, so now. Oh, this is a blast. This is why I know Autumn's going to look at me and go, why didn't you show that earlier? All right, ready? Go to the calculator. What were the numbers? We read that, everyone, we read that statement earlier. What do we have? X was 700, right? How many likely voters? 1,000. What was the confidence level?
95.
We haven't been here before, but everyone, this is one of the coolest buttons on this calculator. Go to the stat button. Go to stat. We've been a stat. But everyone, I want you to go all the way over to test. See, we know where that stat button is, right? Go to stat. You know where we've been many times? You and I have been in the calc. Remember that? One variable stats? This is the first time you're going all the way over to what?
Test.
You're looking for something that has the word interval in it, right? But what type of interval? This is called a 1 proportion Z interval. I'm looking for 1 proportion Z. Oh, this was close, but what does it say? 1 proportion Z what?
Test.
I don't want that. That's chapter 10. I want 1 proportion Z interval. That's a Z interval. I don't want that. I don't want Z interval. I want 1 proportion Z interval. It's got to have that word proportion in it. Where is it? Ooh, thanks, Tia. So I'm going to put A in your notes. 1 prop Z in. 1 prop Z in. 1 prop Z in. 1 prop. Because this is a rock and roll cool button. I'm going to hit it. And this is where you're going to be like, oh, you got to be kidding me. This is going to do it for me? You bet. What was the X? 700. What was that?
Thousands.
1,000. Are you kidding me? Well, now, confidence level, you got to write this as a decimal. Don't put 95. You got to put what? 1.9. And you're like, are you kidding me? Please, and hey, I encourage you to use these. Then you do what? Technically. And you write it down. And you get full credit, don't you? You want to put it all? Yeah, you might round it. You know what we got before? Autumn, I encourage you to use it. It's pretty easy, right? See, what's important, welcome to stats. What's important? Not the tedious look, I bypassed all this. Everyone, I even bypassed that. Do you agree? I bypassed all that. What's important to us is the interpretation. So, can you help me interpret this? With what level of confidence?
95%.
With 95% confidence. Is it the sample proportion or population proportion?
Population.
The population proportion is between what two numbers? 0.672 and look, I barely got any writing. Now I'm going to dig. Uh-oh. Everyone, I am stuck. I am stuck. Because before I wrote it with that plus. Now Mia, here's where we gotta be careful. I don't have that other cool way I wrote it, right? I don't know this right now. See how it's written? So I'm left kind of going off this. Is there a way to get the margin of error from this? All right, how do you do it?
Calculate the mean between add them and subtract from the mean.
That works. And I'm going to draw a picture so you can always get the margin of error. There's a 0.672, and who's on the right side?
0.728.
I draw pictures, we can see what the margin of error. Who's in the middle? Who's smack dab in the middle?
The mean.
Yeah, the p-hat. Remember what the p-hat was? It's up on the screen. Let me hit the light. Do you see it? What's the p-hat?
0.7.
That's in the middle. The margin of error is this number, subtract that number. Just take that subtraction. So Mia, we don't have to do it there. We can just subtract this minus this. Right? Now, you got it. What's 0.728 minus 0.7?
0.028.
Cool. Or if you want, you can take this number, subtract that number. Remember, margin of error means one side. So that's how I'll get my margin of error. That minus that. And put your plus minus, which you get what? And see this? Almost barely any writing. Isn't that cool? Yeah. And then, hey, E, what do you got to do to decrease the margin of error? You got to what? Increase N, and then letter F. Oh, okay. Autumn, you'll probably use that. It's pretty quick. And P hat, Q hat, and your GMAT. You get your 2017. What do y'all think? Who's going to use this button? I would. When I make my answer key, do I use this? Oh, heck yeah. Oh yeah. That's the idea. We know this is available. We could do it by hand, but we're saying, this is what's most important. We know what this means. The article wrote that. Seriously, think about it. Most people read those articles. They don't know what this means. You do. This margin of error of 3%, they're like, I don't know where that comes from. You know. That's what I like about this class. Cool? Hey everyone, super job. Next class we'll do 9-2. Hey, I want to pass back tests and some sheets you can take out.
Keep it.
Keep it.